All right, legends, this is Mr. Mays shooting down the electronic waves to make you a little bit more comfortable with confidence intervals, this time talking specifically not about confidence intervals for proportions. No, my good friends, my students, my pupils, and heroes of the statistical universe. Today we are talking about confidence intervals for means, okay? And as I explained in class, one of the key principles to be aware of for confidence intervals when we understand confidence intervals for means is this sort of tree diagram thing I made for you, which is giving you flashbacks maybe to probability. But good news, you won't have to calculate any probabilities here, and I am just like overfilling, right? Like brimming, that's the word I'm looking for. I am brimming with excitement to share more about means with you when it comes to a confidence interval. Now, if you want to hear initial thoughts on all the excitement and brilliance that you should be feeling regarding confidence intervals, return, of course, to 6.1, where I talk to you about the many universes in which our sample might have existed and the ways in which sampling distributions as an idea transport us into what a confidence interval is doing, which is basically saying, of all possible universes that our sample could have come from, here are the most likely options where we account for 95% of those intervals, 90% of those intervals, 80%, 99% if we're really trying to feel very confident, and so on. So you should already be very hype and very clear on what a confidence interval is and why it's so #dope. Okay, please forgive me for ever saying hashtag unironically. Okay, moving forward. Confidence intervals for means. If I first see a problem on an AP test or in the rest of my life that's a confidence interval problem, it will hit one of two branches, as you know. Option one is proportions, right? P-hat. And that is specifically, you should know, for categorical variables, right? These are variables that are not numerical. And if they are numerical, the numbers do not work together mathematically. Like a zip code, for example, would be categorical, as you might remember, just because it's, the numbers don't add or subtract or do anything. It's a number used for what we call nominal purpose, which is basically just to say, hey, this is the thing, I'm naming it. Right? Or it's going to be for means. And that confidence interval for means will, of course, be quantitative, which means it's numbers, and it's numbers that work together in very specific ways. You can add and subtract, multiply, divide, and that means something to do that. Okay. Once these two branches are established, something to be aware of is that we already know about confidence intervals for proportions. You might remember this from the 6.2 video notes. And for proportions, the things to keep in mind are that the process is relatively straightforward. We go, and we are always going to be doing a one sample Z interval for proportions. That's always going to be the test that we do. And you'll remember that one of the key points of a one sample Z interval for proportions is that we are going to show that this is approximately normal, because what we call our critical value, which is the value that allows us to, I'm going to use my fancy weather term, prognosticate or estimate in theoretical universes all the possible ways that our sample could have worked out. We're going to treat it like the sample is approximately normal. And we're going to take a normal distribution amount of those possible samples, aka the middle 95% normally, or the 99% depending on the interval. And we're going to use that to assume, of all of our different ones, I am 95% confident because 95% of the possible intervals I could have calculated would, contain the true population proportion. Okay, you should be on board with everything I've just said. If, however, we are doing it for means, we have two pathways, not one, which is so wonderfully exciting. Pathway one is very much like the pathway we have for proportions. It would be considered a one sample Z interval for means. And mind you, I'm actually not going to go into too much detail on one sample Z interval for means, because the process is exactly the same as it is for proportions, except for one little tweak. So very quickly, I'm going to go over doing one sample Z intervals for means. This is something I didn't get the chance to do in class when we were doing 6.3, but I will have gone over the next time I see you how to do this calculation. So if you catch this early, you're good to go. All right, and the way we do a one sample Z interval for means, as all of us already know, is we go on our calculator, we are going to click Stat. This is always the sort of process, right? Go over to Tests, you know the whole dealio, as it were. You'll go down to number 7 for tests. It says Z interval. And what the end of it says after those ... is Z interval for means. That's what it's going to do. So click enter on that. And make sure you go over to the stats part and click enter. Don't have it on the data. So just to be clear, not data, yes, stats. And you'll notice it asks for the following things. In order to do a Z interval for means, you need to have the population proportion, standard deviation, that is population. We'll go over that some more in a minute. You might remember from class, but you need to have the population standard deviation. Because you'll remember, in the same way that for proportions, we ended up using sampling distributions standard error, which is the standard deviation of a sampling distribution. We use that in the second part of our equation. And so for means, it's the same deal. It's the z-score times the true population standard deviation over the square root of n, because this is our equation for the standard deviation for a sampling distribution of means, okay? It then asks for the actual x-bar, which is your mean, right, for your sample. And then it asks for n, right, the sample size. And then the C level, which of course should be a decimal and is your confidence level. And then you'll click calculate and it will give you a confidence interval. Okay? Easy process. It follows the exact same process as doing p-hat, except in this case, you plug in the population standard deviation and you do Z interval instead of doing one sample proportion interval, right? Z proportion interval. Okay, very simple process, all the same. And of course, we'll do all the same things about finding the, if you want to solve it out by hand, or if you need to do a margin of error calculation, you're going to do all the same work in order to find your z-score as you would normally do for p-hat, right? You'll do the invert norm. The invert norm calculation. And you'll do area to the left, right? So for example, if I were doing a 95% confidence interval, I know that my area to the left of the confidence interval is equal to the difference between that and 100 divided by 2 to get the upper tail. And so 100 minus that would yield my area to the left, which is 0.975, right? Divide that by 100. Same thing, area to the left, right? And then mean of 0, standard deviation of 1, okay? And that would be how we find the Z value in a mean calculation. And we would use this equation, right? Z times, technically we put the star because it's the critical value, times the population standard deviation over the square root of n. Okay, easy peasy lemon squeezy, everything the same. Now, I want to be very clear. This whole process, this whole thing, I'm gonna circle it, this whole process doesn't happen very often. Not very often. Will you do this? I need you to know how to do it. I need it there, but you're not going to do it very often. Why? Because we do not normally have the standard deviation for the population. In fact, almost never are we given the standard deviation for the population. And there's a good reason for that. So let's think about it for a second. To get the standard deviation of the population, you would have to know how the population is distributed on the thing you're measuring. For example, average height, right? And if you already know that, you probably don't want to do a confidence interval, right? Now, sometimes you're in the lucky position where you do have that standard deviation, and you still want to run a confidence interval to be more sure or less sure of something. But in this case, it's very unlikely that you're measuring a thing, but you happen to have the standard deviation for the whole population, okay? So we enter this sort of new universe. So if I'm going to scroll back up here, okay? Let's do this one in blue. What if I don't have the standard deviation for the population, okay? I can have the standard deviation for the sample, which is what I'll need, but I don't have it for the standard deviation for the population. I only have, and I'm going to call it S sub x, right? Which is the standard deviation for my sample, the single sample I took. And this is much more often the case. In that case, we instead are going to do what's called a one sample t interval for means. So when you do panic, that's what you're going to name it. It's called the one sample t interval for means, okay? Now, I'm going to go through this process with you right now. You will note, if you are looking at your 6.3 slides, right, there is a warm-up and a practice problem, neither of which we got to in class. We may get to it in future class on review day, but you should practice those as you're good. One of them is a power calculation problem, which you might remember from proportion 6.2 work. And the other is just a practice of running panic on a confidence interval question where we construct and interpret it for proportions. The next 3 slides go through all of the homework answers from 6.2. Review those. Be aware on slide number 3 with the first question, number 28. It says, for when I checked for normalcy, right, for my z-score for proportions, I did 0.38 and 0.62. Those are incorrect. It should actually be 38 over 50 and 62 over, 38 over 50 and 12 over 50. But both of those amount to being greater than what we need them to be, right? We take those proportions and then we multiply those by 50, right? So we would end up with 38 and 12, etc., and we would end up with values greater than 10, which is what we need to prove normalcy. Anyway, just a typo there. So we're going forward. We're on slide 6 where we talk once again about what a 95% confidence interval means. That should make sense. I've gone over that a fair bit. And here we go over on slide 8, this idea of, hey, remember standard error? We have these normal distributions. And normally the way we find the distance, as I was saying, in a sampling distribution of possible ways that our sample mean could have happened was population standard deviation over square root of n, right? But if we don't know that, and we can't work with that, we will instead do sample standard deviation over square root of n. So our equation would look something like this. Instead of the z-score, we do what's called a t-score, right? A t-interval, a critical value t, equals our confidence interval for means. And in fact, actually, little typo here, let me fix it. I forgot to write in perhaps the most important part, which is plus or minus, right, the samples mean. Okay. What is a t-interval and what is a t-distribution? Well, if you go up to slide 12, I go into it into a little more detail. A t-distribution is just like a normal distribution, except when your sample size, n, is low, your t-distribution is a lot more uniform. The n's, or tails, as we call them, are larger. They have more of the values in them, unlike a normal distribution where most of the values are in the center, right? And then as n goes up, t-distributions normalize. And what's cool about this is the reason it does this, right? The reason why a t-distribution becomes more normal as the sample size goes up is your standard deviation for your sample will start to act like the true population standard deviation as n goes up, right? But when n is lower, the standard deviation for your sample is a lot more uniform, right? The values are spread out more. There's more variability. And this should make sense, right? As sample size is lower, variability increases. So when we're using the standard deviation for our sampling distribution, for our sample as the standard deviation for our population, well, that just leads to a lot more variability. And so a t-distribution accounts for that and allows us to use that standard deviation to calculate the standard error of a whole distribution, right, a sampling distribution, and therefore look at all possible realities by just looking at one single sample's standard deviation. It's amazing. Okay, hopefully the logic on that makes perfect sense to you, okay? The way that a t-distribution is measured is using df, or degrees of freedom. And you may remember this from forever ago. Degrees of freedom are just equal to your sample size minus 1, okay? You will note that I explained the nerdy reason for this on slide 11, and the reason is that we want, as always, independence. So as you'll see in a second, when we do our t-test, right, and our t-interval, just like when we did our z-interval, for all of this, we're going to check for normalcy because, by the way, a t-distribution requires your same things for a normal distribution, right? You need a t-distribution of all the same rules as a normal distribution because it will normalize eventually. So you need to be able to treat something as approximately normal if you're going to run a t-interval on it, just as you would if you're going to run a z-interval on it. So just keep that in mind, right? Because t requires the same baseline things to be true. But then on the other hand, we have to make sure independence is true as well. And you might remember that like when we're running all of these works for a mean and a sampling distribution, all of the values have to be independent of each other, right? If we're doing a set of means and we're looking at average height in a sample, every height has to be different from every other height. But we have a problem with the t-distribution. With the t-distribution, the way I'm getting my standard deviation is in its very sense dependent on the sample mean, right? And it is in its very nature required not only on the sample mean, but on the sample standard deviation, which actually I can't write as the population standard deviation because it's different. No. We need it for the standard deviation of the sample. And because we are doing that, the way you calculate the standard deviation of the sample uses the sample's mean, right? You have to find the difference of each value from that mean. So for my nerds out there, you're not going to need to know this for the exam, but for my nerds out there, because I have to use my standard deviation for the sample when I do a t-test, and because the way I calculate that technically is by using my sample's mean, every single value in my sampling in my sample is now dependent on one value, my mean. So I have to subtract the place that my mean holds in my distribution and in my sample. So I do n minus 1 or one fewer value. If that doesn't click for you, that's totally fine. Just be aware that when you're doing degrees of freedom, it's your sample size minus 1. And the reason we do it is to keep independence. Okay? For the reasons I stated a second ago. But you don't need to understand those reasons. If that's not clicking for you, that's okay. But just be aware it's to keep independence. And we're still going to do our regular independence check. That's all still in the cards, so to speak. Okay, hopefully you're rolling with me. There's a lot of theory here, but thank you for hearing it out, okay? So what are we going to do in order to run these confidence intervals? Well, the reason why degrees of freedom are so important for a t-interval is because, of course, the more degrees of freedom you have, the more the t-interval is going to run its calculation like it's a normal curve. And the fewer degrees of freedom you have, therefore the fewer sample size you have, the lower sample size you have, I should say, and therefore the more the t-distribution will act like it's relatively uniform. Not exactly, but relatively. Okay, scurry on over to slide 13 with me. We are back to panic. Let's run through what panic says. Part 1 is P, parameter. What's that going to look like? I'll say something like, we are searching for the true mean of blank, right? True mean height in the US, true mean height of high school students, true mean weight of an iguana. I don't know. Could be anything. But state what that true mean is. Okay? And then you're good on P. Check-a-rooney. Slide 15 brings us to assumptions. A. These are exactly the same as the assumptions that we have for a population's proportion, or for a sampling proportion, I should say. Sample for proportions, which we are using for a confidence interval for proportions. Excuse me a moment. Oof, had a little burp in me. It's from this morning's coffee. All right, the assumptions. What are we doing? Random, same as always. Why? Because they said so. It's stated in the question. It must be. Otherwise, it won't be representative. Remember that it is about being representative. That's why we need it to be random. Then we have independence. Why? Yes, of course, I can hear you shouting from the other side of the screen. It must be independent because otherwise we can't look at the distribution in any sensible way and view it as having a specific shape, because certain values would rely on other values and therefore the shape would be kind of meaningless. Independence means, hey, each of these values was accumulated on its own, so they're not directly related to one another. We're just looking at their behavior as an idea, and that's important. What do I need for that? The 10% rule, aka if I take my sample size n, right, and do it times 10, that should be less than the true population size. So if I sample 50 people, I better have a population of greater than 500 that I'm looking to solve for, right? Once independence is set, right, we must make sure it's approximately normal. Again, I will reiterate, even though we are doing a t-interval for this one, right? T-intervals require you to be able to treat something as approximately normal. They just adjust for using standard deviation from a sample, right? By making it relatively uniform and then sloping upward, or I would say more uniform than peaked, and then letting the peak slowly but surely grow into a normal curve as sample size increases, right? What do we do? Well, because we're doing means, we will do the central limit theorem. That is our first option, which is where n must be greater than or equal to 30. Okay, that's option one. Or, and this is all on slide 15, we must say that the population is approximately normal, right? It's all the same rules as treating a sampling distribution, right? As if it's approximately normal. And the last one that shows up less often, but that you might see, is there's just a graph of the sample data. With no strong skew or outliers. And what you would say in that case is you'd have the sample data, like I said, it would look approximately normal, no outliers, maybe a tiny skew, but not a large skew. And then you would just say, please note that the sample data provided looks approximately normal, has no outliers, has no strong skew, therefore we will treat it as approximately normal. Okay, we've done it, legends. We have proven our assumptions. Hopefully you're doing the panic dance with me and Miles, okay? I go over on slide 16 why we check these assumptions, but I also went over that previously, and you should be pretty clear on this by now. But do ask questions if you have them. Slide 17, we have to name the interval. Like I said, n. How do we name the interval? Oh, don't want that. Easy peasy. Name it. It is a one sample t-interval for a mean. Okay, now would be a good time, I just want to clarify for these notes, to go back over everything I have said and make sure that you totally understand it if you're lost at any point in this, right? Because this is a lot of theoretical stuff, and it's a lot of really powerful stuff that should make sense to you at this point. So do go through and make sure it makes sense. And if it doesn't, ask me questions or go through the video notes once again. Okay, up to slide 18, we hit the I in panic, which is give the interval. And that should be relatively easy, okay? The first thing we have to recognize as a side note, okay, before I show you how to do this on your calculator, okay, is that as you see on slide 20, the interval is calculated by, and I wrote this up above, but let's write it again, the sample mean plus or minus the t critical value times the sample standard deviation over the square root of n. Okay, and I want to side note this, okay? For power calculations, and a power calculation, remember, is where you are calculating the margin of error. Be aware I write ME when I was saying margin of error. When you use the margin of error to solve for sample size. Be aware, you will need the mean for the sample, okay? You will need to find your critical value t, which I'm going to go over in a second. And then you will need the standard deviation for your sample, of course, as we know. And then you will solve for square root of n. And really, actually, I should say, you'll solve for square root of n, and then you'll square it. And truly, what you will do is you will solve for n. That is your thing you're looking for. For this reason, I'm going to, side note, for this interval, teach you how to calculate your t critical value, okay? Then we'll return back to how to just run the entire margin of error in a calculator, okay? But it makes good sense to run through and do it by hand really quickly. So I'm hopping. I'm going to take from slide 20. I'm going to jump ahead. I'm going to jump ahead to slide 24. I want you to take a moment and read slide 24. It says example, one sample t interval, and you'll note it begins with the major pollutants in auto exhaust, ... Okay? Take a second, pause the video, read through it, and make sure you're clear. Okay, I hope that pause was beautiful, wondrous, useful. Okay? And so I'm going to start running this calculation. I'm going to do this in green really quickly. Okay? I will note the following things. One, I have my sample size. What is my sample size? N. In this case, 40 light-duty engines is the sample size. Okay? You will note also, I have my confidence level. I'm going to put all my variables down. I like to see them. 0.95 or 95%. I have my sample mean, 1.2675. Always use all the numbers if they give them to you. I also have my standard deviation for the sample. Okay, 0.332. So I'm kind of rolling. I'm doing a great job. The first thing I'm going to do is I'm going to find my t interval because I'm going to solve my t critical value because I'm going to solve this entire thing by hand for you really quickly. Then after that, I'm going to pretend I don't know the sample size and say what sample size would I need if, and then I would give myself a margin of error and roll accordingly. So let's do that. Before we even look at a calculator, I'm going to use my equation, right? My confidence interval will equal my sample mean plus or minus my critical value times standard deviation of the sample over square root of n. Now again, in this case, I'm not doing a power calculation yet. I'm just going to run this equation. And instead of using a calculator, which I'll show you how to do in a moment, I'm going to do it by hand. Let's plug it in. This will be my sample mean, 1.2675. I think my voice cracked there. I'm in my teen years again, y'all. It's happened. Plus or minus t critical value. What do we do for our t critical value? Let me show you. Okay, to find our t critical value, what must we do? Well, you will note that if you go second vars, okay? Second vars. And you'll remember for proportions when we were doing z-scores, and even if we do, z critical values for means, you do inv norm to find your critical value z. For t, you'll go down one more to part 4, which is inv t. Okay? And click enter. That asks you for area to the left and degrees of freedom. The area is going to be the same as what we always do. So for this question, it's 0.95. So what do? I do 100 minus minus 95, I should say, is 5. I do 5 over 2. That's 2.5. You already know all the stuff that's about to happen. I then do 100 minus 2.5, and that yields 97.5. I turn that into a decimal instead of a percent. I'm at 0.975. Okay, so that's my area to the left, 0.975. And then my degrees of freedom, remember, is always n minus 1, not n minus 1. So that will be 40 minus 1, which equals 39. Okay, so in my calculator for my t critical value, I will do 0.975. I will do 39. I will paste and I will click enter. Calculator will chug along. And lo and behold, I should get 2.02, let's say 2.023, okay? 2.02269, et cetera, et cetera. Okay, so that means, I'm gonna erase this so that it's a little bit easier to write it. We got 2.023, and that means that is what my critical value will be. You will note this gives us a different critical value than we would get if we did the z-score for the z interval, because of course this one, because it's a sample size of 40, is going to behave less like an exactly normal curve and will have bigger tails on it. We have our critical value. Be clear on that. That is how you find your critical value t. second vars, inv t, invert t, and then run the distribution. Because what we're effectively doing is finding the area before the critical spot t on a t curve as opposed to a normal curve with a z distribution there, or with a z critical value there. Okay? And then times our standard deviation, I'm going back to my formula now, times the standard deviation of my sample, which is 0.332. I'm going to do parentheses so it's clear, over the square root of n, which is in this case 40. Okay? Don't mix up your degrees of freedom versus your sample size n. When they want n, or when you input n, or when you plug in n, it will just be the sample size. df, or degrees of freedom, will be one value lower than that. Okay? Now I'm going to run my calculation. I'm getting 1.2675. I do this one step at a time on my calculator. If you're running this alongside with me, I do 0.332. I go in my parentheses first, over second square root of 40. And I click enter. I get 0.05249 something. I do that times 2.023. And I get plus or minus 0.106 about, okay? And that, my lovely legends, my wonderful people, is going to give me my confidence interval. So I will make my left and right side of the confidence interval. I will take that value and I will go plus 1.2675. And that will give me 1.37 about, okay? And then I will do 1.2675 minus 0.106 something. And that gives me 1.16 about. And that will be my confidence interval. And then really quickly, just because I really love to do this, it's panic, and we end on C. We'll finish out that before I go over how to do this on a calculator and then how to do a power calculation with it. We will conclude. Same ideas before with proportions. I am, or we are, in this case 95% confident that the true mean, in this case, NOx reading, but that's whatever. You'll plug in whatever the thing is for that particular problem. And I just want to be clear, for light-duty engines. And mind you, the correct way to phrase this is the part that's bolded on slide 24. It says construct and interpret a 95% confidence interval for, quote, mean amount of NOx emitted by light-duty engines of this type, right? For light-duty engines of this type. And I would say is between, and you know how this one goes. You know how this goes. 1.37. Oh, and actually, Mr. Mays did a do mistake, so let's make this clearer. Always put the lower number first, 1.16 and 1.37. And so let me correct myself up here. Thank you to anyone who was shouting, but Mr. Mays, what about the order? You were right, 1.16 to 1.37. Do the bigger number to the right. Just makes more sense. Okay, we have our interval. We have our low and our high end, right? We are rocking. We are rolling. We are happy. We are go-lucky. And we could not be more self-aware, okay? Remember, of course, if we want to find the sample value in our interval, what we will do is we will find the midpoint between the two values in that interval. Same as with proportions, we do the same practice with means. So you would add these two values together, divide by 2, and you will yield around 1.2675, etc., whatever it is, okay? Rock and roll. So we have all of this. Now, side note, you're saying, Mr. Mays, you promised I could do this on a calculator, and you can. So join me. In red. How to do confidence interval for means, for t values, critical values, on calculator. Turn your calculator on. Go to stat, of course. Go over to tests, of course. And this one is never too far off. This one's sitting in your pocket whenever you want it. It's number 8. T interval. ... And what the rest is to say, right, for means, right? Make sure you are on stats, not on data. Don't be on data. Data, no, we don't want to input the raw data. We want stats. Then you'll just put in your mean, your X bar, your standard deviation for the sample, and your sample size N, as well as your confidence level. Be sure to write all of these things if you're doing the calculation on your calculator. So for this particular problem, 0.95 is the confidence level. Our sample size N for this problem on question 24, or on slide 24 was 40. Our standard deviation was 0.3332, and our mean was 1.2675. Let's run this one together, shall we, legends? 1.2675, 0.3332, 40, confidence level 95. Click enter. Let it load. Only click enter once and you will see the exact same interval that we got here, maybe just a little more specific. At the very top, 1.1609. You can include that. You don't have to if you don't want to. And 1.3741. Check a Rooney. Is that not so beautiful, guys? Look at that. So now we know you can do the same process writing this. Now, mind you, at the top, you will have to write T interval. And this, legends, let me highlight it. This is what I expect to see on your page, both on my test and on the AP test, if you're going to run this using your TI, which I recommend you do if you can get away with it, right? If you have all the values, why do it by hand if you can run it with the calculator? That being said, what I will warn you is be able to use this equation, because sometimes they will ask for various things that require just this equation. And you may very well just want to serve yourself in doing so. You can also use this equation to just calculate the margin of error raw, okay? So if we were going to do the margin of error raw, you would just be like, hey, what would the margin of error be if, T is one thing, sample standard deviation is another thing, and our sample size is N. Okay, so let's zoom out. First things first, we don't really have to do power calculations when it comes to means for T distributions because the sample size is going to adjust according to the critical value will adjust according to sample size, so you really never have to run into that kind of problem. But know your formula, know how to use it, because you never know when you want to calculate margin of error by hand. Or you could just find the midpoint and subtract. You now know how to, with your calculator, find a T interval for means, okay? You also know how to do it by hand. You know how to run through Panic for mean confidence intervals. You understand how to check every aspect from the conclusion back to finding the interval itself, as we said, to naming it a one sample T interval for a mean. The assumptions, using the central limit theorem, proving its independence, and going through to make sure that the randomness is present in the question. And you know how to state your parameter. On top of all of that, you understand how degrees of freedom are so important to a T interval. And you understand why we use a T interval and why we use degrees of freedom as opposed to a Z interval when it comes to using the standard deviation of a sample versus the mean. And you know now the breakdown of what even a T distribution is, how it's got bigger, fatter tails in lower sample sizes, and then it normalizes as the sample size goes up. And in the end, you totally understand in every aspect how to go about these sort of ways of confidence intervals, starting with the bifurcation of is it categorical or quantitative, therefore I'm going to do either proportions or means. And then from there, can I do a Z interval for a mean, which just follows the same process as it did for proportions with some caveats, or am I going to go through and run a T interval, which happens much more often. It is almost always a T interval. Just keep that in mind. Legends, I am so proud of you. You are such heroes. From the bottom of my heart, thank you for putting the time and the knowledge in. I know this was a long one, but go through, know it inside out and backwards. Message me with questions. I remain proud of everything that you do all the time, and be aware, confidence intervals for means open up a whole new world, because means are one of the most important metrics we can use, right? A mean is one of the most important parameters we could be assuming things about, because remember, confidence intervals are always pushing for parameters using samples, not the other way around. As always, this has been Mr. Mays, your adoring teacher, signing off.